Okay, so welcome everyone to Paper Club. Today I selected a paper which is about a topic that we haven't really spoken about much in Paper Club, which is generative adversarial networks. They're super interesting machine learning models because they're minimally supervised and they have really large representation power. So what I want to do today is a bit bridge that gap between transformers and GANs, because this paper is about how to use transformers to do GANs. And then if you like the idea of continuing doing GANs, we can find more papers about it. So just because we haven't really done GANs very much, I figured we can do a brief overview about what is a GAN and how GANs are trained. The overall structure of a GAN is you have two models, two networks. One is called the generator and the other one is the discriminator. And the learning objective, so there are two learning objectives that happen simultaneously. The first objective is that the generator model, which you can see down here, it is going to take random noise as input, and this noise it will follow a given distribution. Normally it's Gaussian, but it can be changed. So it'll take as input some random noise, and it'll try to, through several transformations, it'll try to produce an image. And the discriminator is going to try to differentiate between real images taken from data and fake images generated by the discriminator. So the whole process is really interesting because it's a bit of a push and pull, where the generator is getting better at fooling the discriminator, and the discriminator is getting better at not being fooled by the generator, which is a real challenge. So the process is really well illustrated here. So through the training process, what happens is that the generator becomes better at creating images that look realistic. So the discriminator cannot tell the difference between real and fake images. The training process is actually very simple. So what happens is that you train either the discriminator or the generator, and you train them separately. So you start by creating the discriminator loss, which is basically a classification loss. So you give it real images and images created from the generator. And the discriminator is going to, so the back propagation is going to be with the discriminator being able to classify an image as real or not real. So you do that for a few epochs, and then you fix the discriminator and you switch to training the generator. And now the objective of the generator, which is going to be the generator loss, is to create outputs such that the discriminator always says that the images are real. So these two losses are different and they're not used simultaneously. So you use one loss or another loss depending on whether you're training the discriminator or the generator. But what's interesting is that so whatever the discriminator learned during its epochs is going to affect the training of the generator in the following epochs. And then when the generator learns some more, then the discriminator is going to now have to change its weights to adapt to the new generator. So this is a very interesting process, and it has some really interesting, some really cool applications and some really interesting applications, right? So one of the, on the interesting side is, for example, you can train the generator to be conditioned on text. So you can see it, for example, generating images from text. You can actually train a generator to generate language as well. And then the discriminator will try to tell if the language is real or not. So you can create language models using a generator, so language generating models. And just as a testament of how powerful this training procedure is, in this paper, which is called, it's so unsupervised representation learning, which is not the paper that we're going to look into today, but one of the interesting things that they see is that so they do these arithmetic operations with the noise. So if you take that input vector, so call this input vector Z. So they take the Z vectors that produce images of smiling women and then of neutral women and of neutral men, and they average them to produce this. So they average the random vectors, right? And when you average the random vector, the generator can still produce an image that looks realistic. But what's interesting is that when you do arithmetic operations with the random vectors that produce these images, you can do things like what you do with word embedding. So if you subtract a neutral woman from a smiling woman and then you add a neutral man, you get a smiling man from the generator. So in this case, the central is the one that's generated with the arithmetic operations from the noise, and then the surrounding ones are with by adding Gaussian noise. So it just speaks about the how these networks are capable of learning how to convert noise and how to do it meaningfully, right? So noise representations start actually having meaning. You can see the example with the glasses as well, which is also quite interesting. So now we can, so I hope that is clear. That's a really broad overview of GANs. GANs have been traditionally dominated by convolutional networks. The first GAN was actually just, so these were just fully connected networks, the generator and the discriminator. But now they are almost exclusively convolutional. And that's what brings us to the paper today. So there are two main limitations that they describe here. So the main known limitation of GANs is training stability. So this process, so you basically have to monitor the discriminator and the generator loss until they have both plateaued. And that's when you say that both models are ready to be deployed. But this process is notoriously unstable. So it is really hard to get both models to learn. And normally you have to do a lot of engineering in the training process and add data augmentation and add a lot of regularization. So that's the main problem. And actually that's how they start the paper, by saying that this is a really hard process. So this is a really hard process. I guess this is where the main criticism comes to the paper, because they open with that and then they don't actually address that problem. They still say at the end that the process is still unstable, but well, you can't have everything. And then the other big question mark that the authors made about GANs is that no one ever questioned that convolutional networks are the best architectures for GANs. And what they say is that, well, the main disadvantage of using convolutions is that you have this trade-off between the receptive field and then the complexity of the model. So if you keep the network short so that it is easier to train and this GAN process is more stable, then you lose the global statistics of the image. But if you make the networks deeper so that you're starting to, so you increase the receptive field of the convolutional networks and you start to capture more global statistics, then the training becomes very unstable. So there's a bit of a trade-off there. And what they say is that, well, if we can replace convolutions, we can maybe get rid of that problem. Can you still see my screen? I can't see the, yeah, okay. So if you get rid of convolutions, you might be able to get rid of this receptive field problem. And of course, what they say is that the most popular architecture right now are the transformers. And the transformers are being sold as these generic architectures, like they can be adapted to almost any task in machine learning. And one of the main motivations that they say about using transformers for GANs is that they don't have this inductive bias of locality. Like they have, because they use this global self-attention, they can learn locality if they need to, but they will also be taking into account the global statistics. And this is one of the most important claims of this paper. And we will see later on that technically they do achieve this global, so this model that learns global statistics, but not quite. Like they still have to put the bias of locality at some point in the training. But it's still interesting how they justify it. And yeah, they speak about transformers as being a good way of getting rid of all these, they call it ad hoc blocks that you have to put on CNNs to make them work for GANs. Again, they still have to do a lot of fine tuning in the training process, but those are the main claims, and that's what they say are their main contributions. So you have a model architecture, which is a generative adversarial network that does not use any convolutions. We'll see there's a bit of a caveat to that. The training technique that they developed is completely new. Well, not completely new. They kind of recycle several different strategies that are used for GANs, but they build a new pipeline that is suitable for training transformers for these GAN tasks. And they also take advantage of the large amounts of data that are available to increase the state of the art in some data sets, not in all data sets. But again, it's an interesting development that transformers are yet again taking over a field that was dominated by some other architecture. So it's interesting to see how transformers are actually looking like they are becoming these like go-to architectures for whatever task you have in machine learning. I think that another contribution that is a bit undersold in the paper is that they make these architectures very tractable in memory and time. So even though they're using transformers, you don't need a million GPUs to train them in tractable time. So we'll see what that is in a moment. Okay, are there any questions so far? Comments? Okay, cool. So like I said, the main motivation for this paper comes from the vision transformer, so this is the vision transformer. An image is worth 16 by 16 words, and we can go back to the paper. So what the vision transformer does, sorry, okay. So what the vision transformer does is it deals with the high dimensionality of images. So let's remember that the big problem with transformers is that you need to build this self-attention matrix, and that scales with the square of your sequence length. So in an image, if an image is 64 by 64, your self-attention matrix becomes massive. So the way the vision transformer deals with this is not by changing the transformer architecture, but just by defining these patches of images. So if you have a big image, you divide it in well, they do 16 by 16. So they divide an image in 16 by 16 megapixels. And then what happens is that this megapixel gets a single spot in the self-attention matrix, and then this one gets another spot. So this megapixel, so all the pixels in here are going to be attending to all the pixels in here, but these all have the same weight. So the self-attention in that sense is made in patches, and that just reduces the size of your image, especially if it's a high quality image. It just reduces it to a size that is similar to a sentence. So then the transformer becomes tractable for images. What they do here is something similar. So you have these transformer blocks, which are what I just said. So they take in these megapixels and they apply the self-attention in those megapixels. However, this vision transformer is still very large, and here's the first contribution that they make is that they don't use the off-the-shelf vision transformer, but they do this upsampling thing. So it's an interesting architecture because it allows them to deal with the explosion in dimensionality. So what you have is you have your noise input, which is of dimensions. What are the dimensions? I think it's 8 by 8. Well, they have a given dimension, and then You have this 8 by 8 by C. So C is just an arbitrary vector, which you just need to make it such that these divisions are possible. But it's like, imagine you have an 8 by 8 image, and then you have a number of channels, which in a real image, it would be red, green, blue. Here it's just going to be an arbitrarily high dimension vector. So you have your 8 by 8 patches, and you have all your channels, and then all the channels are going to take the same attention weights. And then you put it through the transformer encoder, and you get a hidden representation here. You get a hidden representation of your noise. And what you do then is you do an upsampling using this pixel shuffle technique. So let me see if I can zoom in. Okay. It doesn't really zoom in very much. Can you see this image? Can someone tell me?
Yes.
Okay. So if you have an 8 by 8 image and you have a number of channels, what pixel shuffle does is it unravels these channels. So it unravels in the dimension of the channels, and it creates a higher resolution image with less channels. So the dimensions are very well defined. So when you do pixel shuffle, you double the resolution of your image. So it becomes 16 by 16, and you divide the number of channels by 4, because you need to put like a few pixels around a few channels. So you convert channels into pixels of the image. Yes, Peter.
One thing I was thinking about this part of the, so as you pointed out, one of their arguments is that you have this explosion in computation time as the size of the vector that the transformer encoder is processing increases. It's like it's quadratic.
Yep.
And so they're saying our technique, we don't have to actually have these massive vectors for images. But then if you look at the architecture they're using, they actually are using a transformer encoder on the layer on the largest size of the image. There's no upscaling afterwards. So I was feeling like that claim isn't well substantiated by this approach, because I feel like there should be an upscaling layer, at least one upscaling layer above the last transformer layer, for you to argue that you're not having to deal with this like really large vectors in your transformer encoder.
Yeah, so the argument is that these encoders are smaller. So the save in dimensionality is that these don't all have the same size. And actually the one that has the most encoder layers is this M. So we can see later in the hyperparameters, this is like 5 encoder layers, and these are like 2 and 2 for the.
Okay.
So that's where they save a lot in dimensions. Like most transformer architectures, they will just stack the layers one on top of the other. So if you have 5, 7, 9 transformer layers, all with the same size, then you have all those. So you have all those self-attention matrices, which are all squared with the size of your image. So that's where they save in dimensions.
Yeah, I guess I was thinking like you couldn't use that last transformer encoder layer if the image was like, I don't know, 600 by 800 pixels though. Then
yeah,
it would.
But also remember that this is a vision transformer. So every pixel is, so this is going to be divided in patches as well. So it is not going to be every pixel attending to every other pixel. They're going to be in these like patches of pixels. So yeah, it is using a couple of techniques. Cool. Any more questions, comments? Okay. So what happens at the end is that you get your generated image. So of course they put a dog here, but this image at the beginning is going to be completely random, and then the generator is going to get better. So this is going to be this output, right? So the output of the generator. And for the For the discriminator, they don't actually need to do anything fancy. They just use a vision transformer because they already have the image in the correct resolution, or the fake image in the correct resolution. The discriminator just needs to use a vision transformer. So this one is going to be big, but as we will see later, the discriminator is actually a lot smaller than the generator, and you can get pretty good discriminator performance with small transformers, which I found interesting. So that is the architecture that they are using. As we will see, like it would be great if this worked right off the shelf. But they call it, in the methods, they call it a journey to the transformer GAN. And you can see in this table that just this naive implementation, it doesn't do better than the state of the art, which I guess was their initial intuition, was that they would just put 2 transformers and train them, and then that was going to be it. But it's actually not true. What they found does best in inception score, but not very significantly, is to actually use the transformer for the generator and then AutoGAN for the discriminator. So AutoGAN is a convolutional based GAN. But then again, what they want is to do a pure transformer architecture, right? And they start. So here's where the tricks in the training start. So the first thing they do is this data augmentation technique, which is actually quite interesting. And if you want to know more about it, here's the paper. So it's called differentiable augmentation for data efficient GAN training. And what's interesting, so what they've realized with GAN is that if you do data augmentation, the training becomes more stable, and you also get better generators and discriminators from the training process. So what this paper proposes is that you don't do the traditional data augmentation and then train, but you include the data augmentation within the training process by using differentiable functions. So there are 3 functions in diff augment. They are called, oh, I can't find them now. I had them inside. Well, there are 3 different functions, and they are here. Okay, so you have translation, cutout, and then color, and saturation. Also, there are 4. So you have those 4 operations. They are actually applied within the training. So you can see that it is, so the output of the generator or discriminator is augmented. So this T function is the diff augment, which means that the data augmentation is within the training process. This has 2 advantages. The first advantage is that you don't need to pre-generate and save all the images. They will just be generated during training. And then the second advantage, and obviously the main advantage, is that it makes the training a lot more stable. This is not a contribution of this paper. This is just something that is used in GAN literature. What is interesting about the paper is that they showed that the pure transformer GAN actually benefits a lot from this data augmentation. And their intuition at this point, which they say it's confirmed later, I think it's a bit shaky, their confirmation, but their intuition is that it's because transformers are so data hungry, like they need all these data points to create good representations, that augmenting data and giving the transformer more training examples is actually helping it improve. And in fact, the data augmentation just makes the results a lot better, but they are still not state of the art. So this style GAN, which they call heavily engineered, I haven't gone into this paper, but they say this is heavily engineered. I don't know where they draw the line for heavily engineered, but we'll see that there are more things to this architecture to bring it to state of the art. So yeah, so far we have the speed up for the transformers, so making sure that the parameters don't explode, and we have the data augmentation, and we are edging forward a bit in the state of the art, but not quite there yet. So next thing they do, and if someone has seen this before, it would be cool if you intervene, because I didn't quite get how the whole process works. But it's this idea of transformers being trained on two different tasks. So if you take BERT, it is trained both on token prediction and on next sentence prediction. So it's simultaneously training. So they do something similar here. So you have the discriminator, so the generator loss, which comes from the discriminator being able to tell if the images are fake or real. And then they do this super resolution task, where at the second stage, they input a real image, but downscaled in resolution. And then the GAN has to try to predict the high resolution image. And then you compute the MSE. But it is not clear to me how this is, how is it input at the second stage, and how is it possible that this is not fudging the other metrics? Joao, promote to panelist.
Yeah, so does this mean that the stage one in that image is trying to generate a low resolution image, and then the other two are concerned with refining the image in the addition?
Yeah, so that's the idea here, right?
Yeah.
So the idea of the architecture is that you start with like a low resolution noise and then build the high resolution image. But I still don't understand where this comes in.
So it seems like the first stage is trying to create some like legit representation of the world, and then the other two stages just are good at upscaling things.
Yeah.
Maybe without this, the like parallel training, they wouldn't get as good as at creating high resolution images. Makes sense.
Yeah. Yeah, it's still weird, because normally GANs don't get to see the real images. So the generator never gets to see the real images. So it just processes the noise, right? And now you're saying that in your co-training task, you are giving it the real images and just asking it to give you a higher resolution version.
Yeah.
I mean, I guess it's possible, but they don't explain very well how they feed this image. Or if they get rid of the noise, or if they average it somehow. They just say we feed the low resolution image, and then we measure the mean squared error with the super resolution.
So the training is being done at the same time. So when it is trying to create an image to fool the discriminator, the image, wait.
Yeah.
So how do they link the two training processes?
So there is they have an extra loss, so this super resolution loss, but they're not clear about what happens, because I don't know if it's that, that you have this this red line here that goes into a discriminator, and then a separate run that goes to the super resolution.
Yeah.
Or if they actually, because if they input the image here, then it's cheating, right?
Yeah, it's getting a lot of information, but I suppose that at inference time, they don't input any image at all. So maybe there are like two kind of separate processes. They just share weights.
Yeah, perhaps. So yeah, it's definitely not clear. So we can speculate a bit how this is done. But anywho, they show that it improves a little bit their own. So they have the transGAN with data augmentation, and then they call this multitask. No, well, they add this multitask code training, and it increases a little bit. I don't think this is enough to be significant, which is interesting. It just means that it's getting better at creating high resolution images, but I mean, the inception score also measures the quality of the image. But well, anyway, it helps a little bit. And then what really gives them a further surge, and this is where their first contribution becomes a bit shaky, is that they do this locality aware initialization. And what that means is that, so they say, okay, transformers don't take into account locality, but we think that locality is important, at least at some stages of training. They say that at the early stages of training, you need to force the network to learn the importance of locality, otherwise it's not going to produce good high resolution images. So they use this mask, which they gradually expand. So in the early stages, it's just like the transformer is only allowed to attend to the local neighborhood, and then in the middle stages it can attend to a bigger portion of the image, and then in the final stages of training it can attend to the whole image. Which, fair enough, it's not a convolution, but it looks a lot like a convolution. And I don't know, I interpret it as putting back in the inductive bias. It is true that at the end, the transformer is attending to the whole image. But you are acknowledging that the CNNs do have a reason to be there, and that the idea of locality is important, and that it is an important inductive bias in the process. Are there any comments about this? Did I offend someone? Okay, cool. So yeah, so that's what they show here, is that with this local initialization procedure, they actually get a significant improvement from just data augmentation. So again, this is interesting, but it is still not state of the art. The state of the art is this StyleGAN v2. And they actually don't make an effort to improve state of the art on, so these are on Cypher 10, and they don't make an effort to improve the state of the art on Cypher 10 because they say, so they hang on to this idea that it's because transformers are so data hungry, so data intensive, that they need more data. So instead they go to this second benchmark. Oh, well, sorry, yeah, here's what we were speaking about before, about dimensionality. So as I think is regular with transformers, the bigger dimensions actually lead to improvement in performance. So this is the initial dimension that they're using. So these are the number of layers and the hidden dimension. So it is a small transformer. And they show that on Cypher 10, it takes 2 days on a few V100 GPUs, which is crazy, because that is absolutely no time for training transformers. Where is it? Yeah, here. So they use 4 V100 GPUs, and it takes 2 days on Cypher 10, and 3 days on the other data sets, which is actually really fast for transformers. So that's great. That's a really cool contribution. And of course, the larger models do take longer to train. So yeah, so the final note is that, yeah, on Cypher 10, they don't achieve state of the art, and they attribute that to the fact that Cypher 10 doesn't have enough training examples. So even with the data augmentation, it's not enough training examples. So they go to this other benchmark called STL10. And this is twice the size of Cypher 10, and there they do achieve state-of-the-art results, so by quite a margin as well, with their largest architecture. So that's actually
the StyleGAN is not there, right? The one that
No.
achieves state-of-the-art on the other table.
No, it's not there. But this is the current state-of-the-art here.
Mm-hmm.
So yeah, that's cool. And then again, they say that this is because this is because they say that this is because this data set is larger and transformers are data hungry. My question here, so my only question mark on this is, well, they could have subsampled this data set and see if the transformer loses performance, right? And then they would actually say that it's because of the data set size and not because of the not because there is a bias in the process that helps this data set. So that's my only big comment on this paper, is that, well, yeah, you're making this big claim about data, but you're not quite proving that is the case. And I just think it's cool to look at the images. Like, you can't really see them well in the paper, but you can see that the faces are quite realistic. And yeah, if you look at the images, they're also quite realistic. So that's the other cool thing about the paper. They do list some limitations, which is fair enough. So which is more like a laundry list. It's like, okay, these are, now that we know that transformers can be used in this setting, we can actually try more interesting things, like improving the self-attention in transformers. This conditional image generation task, which is so that here they do this on conditional generation, which is just give random noise and see the image that the generator outputs. But with conditional image generation, you want it to produce something specific. So you can give it a text input, like produce a dog, or produce a flower, or produce food, and see that the output is coherent with the input. And yeah, that is overall, that is the paper. My overall thinking is that it's quite an interesting paper. It's a very simple idea to use transformers, and I like the fact that they include knowledge about transformers and how transformers learn to improve the training process. So it is a shame that they start with such a strong claim that transformers do not require any inductive biases, or that transformers are very general architectures and they can learn anything they want. And then they have to do all these tricks in training to actually get them to do something useful. I think that it's a shame, because at the beginning the paper seems very exciting, and then you're like, well, okay, then. I mean, it is a good contribution, but it's not as big as you made it sound in the introduction. Cool. Other comments, questions about the paper? Do you like GANs? Is it something that you would like to see more of? It's just...
One thing I always wonder with papers like this, where they have like quite a few steps which add to create state of the art, is like, one question I have is like, how many more parameters does Transcan XL have? Or is it equal to the baselines? Because I don't know, I think one of the reasons why transformers are so successful is just because it's a good way to train a ton of parameters altogether. That's simplifying things a lot, but like, and then another question I had along the lines of this was like, how much hyperparameter tuning and do they have to do to find these models, or how robust is it are there results to hyperparameter tuning? Because I know you mentioned that GANs have like this issue that they're pretty unstable and you have to do a lot of hyperparameter tuning basically to get good results. But I mean, then how transferable are the contributions that you see here? If like you have to do this really specific approach and you have to search for this really specific performance, and then in general, it just doesn't perform that well. I don't know, that's always when I see like, here are 3 techniques we added to our model to get it to work really well, and then we're also using a huge model. It's like, are these contributions generalizable, or is it just that you did a really good hyperparameter tuning better than other people have done, and you have more parameters in your model?
Yeah, that's a good question. I don't think it is answered in the paper. They do speak a bit about hyperparameters, and they say that there is not much tuning to be done in the hyperparameters, but they don't compare the number of parameters with other architectures.
Mm. I agree with you, though. I like even though it kind of uses that locality assumption that you see in convolutions, I do like the technique of increasing the receptive field. It's kind of like start with an easier problem and go to a harder problem.
Yeah, it's funny because they really bash against the convolutions in the introduction. And then they're like, well, maybe at the beginning it is convenient to treat it as a convolution, and then you relax that assumption. Which is, I mean, it happens. It's part of the process. I also go João.
I really like although it's not detailed, I like the parallel training objective of trying to make sure the network knows how to upscale information. I think that's good, because then you can separate like the network. So this part of the network is to generate a new image, and this part of the network is to upscale that generated image. And I think this like a distribution of tasks makes sense, especially when you can augment and fine tune them individually.
Yeah, that is really so it is a good idea. I should say that it is also not a contribution of this paper. So even convolutional networks, they also that's why GANs are always they're always depicted in like this conical shape. So the generator always increases the size of the output until it's at the target resolution, and then the discriminator decreases the size of the output until it does the classification. So they just made it smart so for transformers. But it is a cool idea.
I like the paper. They do have the code available as well. I just am looking through it, but I can't answer any of the questions that people have raised from that.
Kind of. Oh yeah, the code is available, and yeah, the other thing that Peter said in the chat is I forgot to mention that GANs. So that's the other big problem with GANs is mode collapse, which is that they just learn to. So they always produce very similar images. So it's not really a general generative model. It's just taking noise and producing always the same thing, which is a big problem. It's part of the instability of training. And it's also why they use these very qualitative assessments sometimes. So they say like the images produced are like visually pleasing and diverse. Which is completely qualitative, but it's actually a strong indication that the GAN is generalizing and not just producing the same image all the time.
This is kind of a like, I don't know. Have you ever read about variational autoencoders?
Yes.
Okay. If you had to choose between using a GAN and a variational autoencoder to like create images, to create a generative model for images, which one would you choose? Like, I know it's kind of it's kind of a very blue sky question, but just curious.
It would depend on your budget, wouldn't it?
Yeah, I mean, GANs are just better, right? VAEs are simpler models. So if you have the resources to train a GAN, I would go with a GAN, but then you need to be patient and be careful about your tuning.
Yeah, I guess going back to this, and it's definitely a personal bias of mine. It's just like when you have a model where you basically have to do random search to figure out what to get the best results, it's I always like that technique a little bit less because of it, because it's like it might get the best results, but yeah, there's this random search element to it. But anyway, I do think the training process of GANs is very intelligent.
Yeah, that's a fair that's a fair concern. So one of the things that they do in the paper is that they also say that, so they say that they make it a point to say that they're comparing to the numbers reported by others with their hyperparameter tuning. So in this paper, they are not making an effort to tune the other methods. So they just tune their own method to have a better state of the art. So I guess, yeah, that's a question mark, but you can never know, right?
Yeah, and who has the time to do hyperparameter tuning on all their baselines?
Indeed. Cool. So GANs seem to be popular. We can try to find more interesting papers. I'm pretty sure this paper has not been published yet, but it's on archive. So, and the code is available. So feel free to look into it. And if you produce some interesting images, send them over, and we can showcase them here in Paper Club. Okay, so thanks everyone for attending. And as usual, if you have any ideas for papers that you would like to present or that you would like to discuss, please send them our way. We'll be more than happy to put them in the rotation. And yeah, see you next week. Bye, everyone.
Thank you,
Very much.
Carlos.
Thank you, Carlos.
Thank you.
Bye.